So we've been talking about chapter 15 here, which is solutions. So remember that as we talked about, really a solution is made up of two different things or two components. A solution is made up of the solute, which is the smaller part, and also the solvent, which is the larger part of the solution. Again, both of those things together do make up a solution, which is a homogeneous mixture. It is the guys in the formulas that get the aqueous symbol next to them. So those are, again, those guys that typically have that aqueous symbol next to them. Now, remember that a lot of times water is a solvent, but it doesn't always have to be the solvent. And usually the name of whatever solution it is will be really what the solute is. So as we talked about last time, if we have a sodium chloride solution, the solute is going to be sodium chloride. And really, most likely in this case, and with a lot of ionic compounds, probably the water here will be the solvent. We also talked about sort of solubility, and really a lot of how things are sort of soluble in each other, as we talked about, really does depend on sort of the intermolecular forces that basically are interacting there. So a lot of solubility depends on the idea of like dissolves like. And that's the idea of things that have very similar intermolecular forces will typically be soluble in each other. Things with very sort of different sort of intermolecular forces typically tend to be sort of insoluble in each other. Really, the major sort of intermolecular forces that we talked about, we talked about hydrogen bonding, which is a bond between hydrogen, nitrogen, oxygen, and fluorine. And this is typically used for polar molecules that basically have that bond of hydrogen to a nitrogen, oxygen, fluorine. Again, that bond will create a really polar bond, and really all intermolecular forces, as we spoke about, are really just a basic positive, negative attraction to each other. So by having this sort of polar group here, it allows it to interact really well through hydrogen bonding, and it makes a really strong sort of interaction that occurs. There's also dipole-dipole interaction, which is how also polar molecules basically interact with one another. We typically think about dipole-dipole for guys that really don't have the ability to hydrogen bond. So they'll just use a basic sort of dipole-dipole interaction, which is, again, with a polar molecule. It has a dipole moment, which means, again, there's a positive side and a negative side to that molecule. And again, that is how they're going to be able to interact with one another. The last sort of intermolecular force is one that's known as dispersion forces. And these are really how sort of nonpolar guys interact with nonpolar guys and themselves. And these are very weak and temporary type of attraction forces. So remember, as we talked about a little bit, they sort of depend on, for example, electrons sort of moving from, say, one side of the molecule to another. Also, maybe somebody could induce that to happen. But it is dependent on that sort of temporary sort of dispersion of the charge on that molecule. They don't always have a positive side and a negative side. Again, a nonpolar molecule would mean that they really are overall sharing electrons equally. But with dispersion forces, what can happen, again, those electrons can kind of go one way or the other and temporarily create this positive negative side, which allows them to interact with other nonpolar molecules, again, being very weak as they can kind of move back and forth. So then in terms of sort of the strength here, this is really the strongest. And this is really sort of the weakest sort of interaction. So when we put things together, like polar things and polar things, or ionic things and polar things. It's really the sort of interactions that help us understand if things will sort of mix together or not mix together. And really what we get with that like dissolves like is the idea that typically things are soluble if you kind of do an ionic and polar things together. Again, ionic and polar are going to be able to do some type of dipole-dipole interaction, and they will be able to positive and negatively be attracted to each other. If you have polar and polar things together, those things will also be able to interact well. They would either use dipole-dipole with each other, hydrogen bonding with each other, and also the one that sometimes, as we mentioned last time, is sort of overlooked by people, nonpolar and nonpolar guys are also going to be sort of soluble in each other. Again, they're both going to be using dispersion forces, which will allow them to, again, interact well with one another. Pretty much the roadblock in terms of solubility is usually when you kind of cross over and try to do some nonpolar polar interaction. Again, you usually run into a roadblock here because our nonpolar guy is going to use dispersion forces. Our polar guy is going to try to use some type of hydrogen bonding or dipole-dipole interaction. And as we talked about, over the long period of time, there really is no way for them to maintain a really good sort of attractive force with one another. So they typically will separate out. So as we talked about, if you had two liquids that were sort of opposites of each other like this, you would see some different layering, which maybe you saw in the experiment the other day. Also, if obviously you took a solid and a liquid and you try to mix it, the solid would probably not dissolve because there would be no interaction. Yes, sir. That is true. Yeah, exactly. That is exactly right. So as we talked about last time, we saw that sort of oil and water, an example of that as well. They will definitely separate out. So we also talked about ways to describe solutions. You could have a saturated solution, which is a solution where you basically have the maximum amount of solute that will dissolve at a given temperature. We also could have an unsaturated solution where we really haven't hit that point yet, which means, again, you can continue to dissolve more solid in it, and it will continue to dissolve until you really do hit a saturated solution. And as we saw in sort of the demo there in part A of the experiment, you can also have a super saturated solution, which we also talked about, where, you really do have too much solute sort of dissolved in that amount of solvent for that particular temperature. And as we saw, it was a very sort of unstable solution where it just took like a very small amount of that solid that you put in there, and that was enough to sort of force everything to come out of solution. We also talked about concentrated solutions, which obviously have a much larger amount of solute dissolved than a dilute solution. Then we got into some concentration sort of units, and there's percent mass to mass, which is the mass of the solute divided by the mass of the solution times 100%. We also saw a couple of other ones, percent volume to volume, which is the volume of solute divided by the volume of solution times 100%, and percent mass to volume, which is the mass of the solute divided by the volume of solution times 100%. Remember, though, with the mass percent, that bottom part is really important. Again, in a lot of problems, they will really break up the solute and the solvent in the problem. So you want to make sure that you really do get the mass of the entire solution and not just the solvent, which is a very common mistake. We ended last time talking about molarity, which is really the most common unit of concentration. Molarity is moles of solute per liter solution. And we can rearrange this equation. Liters would be moles divided by molarity, and moles would be liters times molarity. When you do have a solution in terms of its molarity, if you had a 3.5 molar calcium chloride solution, it's really important, as we talked about, to sort of pull that M off of it there and really sort of use both of the units in your calculations. So you could do it dimensional analysis way. And as we talked about, so you do not lose the volume, which is again a very common sort of problem for people. That basically means that there are 3.5 moles of calcium chloride per liter solution. Or if you wanted to use it like a conversion factor, you can flip the liters on top and use 3.5 moles of calcium chloride. It is really highly recommended that you do it that way, again, so that you see both of those units, because again, a lot of people have no clue where the liters part is or if there is volumes. And it is a very common mistake that people see that big M and they just think, again, moles. And again, there's actually 2 units in there and you do want to look at it. Typical conversions that you have to do a lot of times when you're dealing with molarity is grams to moles using the molar mass from the periodic table. And also a lot of times volumes are given to you in milliliters. So the 1,000 milliliters to a liter is a very common sort of conversion as well. Any questions on that there? Okay. All right. So this is also something that we talked about as well, which is the idea of how molarity relates to the ions. So why don't you try this? These are 2 separate solutions. So in the first one, we want to know what is the concentration of just the sodium ion and what is the concentration of the sulfate ion in that solution. And for the second one, we want to know what is the concentration of the potassium and what is the concentration of the chromate here. So take a moment or two, remember what we talked about, how the whole thing relates to each of the individual ions, and see what you come up with, and then we'll talk about it. Okay, let's take a look. So as we talked about last time, you really want to, when you're interested in, say, just the ions that are present in solution, because these are ionic compounds, pretty much when that thing is, in solution, what you really have are sodium ions floating around. You got some sulfate ions that are basically floating around in solution. Remember that they're sort of strong electrolytes, which means they're not really staying together. They're going to break apart in the solution and float around. So sometimes you may be interested, again, like I said, in just the individual ions that are floating around. So we could basically want to start with really how this thing would break apart in solution, and it would break apart into 2 sodium ions and a sulfate ion, basically. And really the quick way, as we talked about in terms of how you can relate molarity to the individual ions, is if you do know the entire concentration there for the intact unit, if you will, you can basically just do very much like a stoichiometry problem. And we see that for every one of these whole things, we get 2 of the sodium ions. So you basically would multiply the concentration by 2. And that would get you 2.4 molar would be the concentration of the sodium ions that are floating around in there. You could also do the same thing for the sulfate. It would be basically a 1-to-1 relationship in terms of the sulfate and the entire thing. So basically you would multiply the concentration by 1 in this case, would obviously give you 1.2 molar. As we talked about last time, obviously they don't add up to the original concentration. But if you think about just logically when it goes in, you basically get 2 sodiums for every 1 sulfate. So it's twice as concentrated in terms of the sodium than it is the sulfate there. A reminder that sort of the longer, more proper, if you will, dimensional analysis sort of calculation of this. I'll just show you one of them for the sodium. You typically would start with the 1 point, maybe if I get something right with, I would start with it. Sorry. There you go, 1.2 moles of the entire thing per liter. And that's basically what this number represents. And basically you would do just stoichiometry like we were just talking about. It is a 1 mole to 2 mole relationship. So you would do 1 mole of the entire thing is 2 moles of just the sodium ion. The moles of the entire thing cancel here, and that is basically how we get our 2 to get it to 2.4 moles of sodium per liter. And that's basically where the multiply by 2 comes from. So that's sort of the shortcut to the sort of dimensional analysis approach to it. Any questions on that there? All right, looking at the second one, which I forgot what was it there, 0.075. So we got K2CrO4, 0.75 molar. So in this particular case, this guy would break apart into 2 potassiums and a chromate. So once again, we can just apply the quick move, which is a 1-to-2 relationship here for our potassium. So we're going to multiply the molarity by 2. And when we take 0.75 times 2 gets us 1.5 molar for our potassium ions. And it would be a 1-to-1 relationship here, excuse me, between the chromate and the potassium chromate. So that'd be 1 times 0.75 molar, which obviously would get us 0.75 molar for our chromate ion. And this would be obviously our sulfate here. And that would be our sodium. Any questions on how to relate molarity for the entire ionic compound to the molarity of the individual ions? Now, you don't necessarily have to do this in every calculation. It obviously would be a specific question where they just want to know about a specific ion, not the whole thing. So obviously, if it's the whole thing, you don't need to figure out the ion concentrations and stuff like that. Any questions on that there? Okay. So why don't we try one like that? We want to know how many moles of sodium ions are present in 42 milliliters of a 0.35 molar sodium chloride solution. So take a moment or two, see what you come up with here. All right, so let's take a look. So first off, we are really dealing with molarity, which is moles per liter. So if you're not sure really where you should start, you could just kind of check off what's given to you. We have a volume, although it's not in liters, we definitely could get it into liters. We also have the molarity given to us. So it would make sense, obviously, here that we are going to be shooting for moles. If you rearrange your equation correctly, moles will equal liters times molarity. So we do need to do a couple conversions here. We can straight up start with our volume. And again, very common conversion. There are 1,000 milliliters in a liter. The milliliters here will cancel. That's going to give us 0.0420 liters. You 100% of the time, just to be safe and always be safe, if you're using molarity and a volume, just make sure it's in liters, all right? Because otherwise you will probably be off based on what you're looking for. In this particular case, though, we are interested in really just the sodium ions here, not the entire thing. So what we might want to do here is figure out, once again, something like sodium chloride would break apart into a sodium ion and a chloride ion. And in the case of sodium chloride here, it is 0.35 molar, which means it is a 1-to-1 relationship between the sodium ion and the entire thing, which means 1 times 0.35 molar gives us 0.35 molar of the sodium ions. So in this case, the concentration is the same because it's a 1-to-1 relationship. Also, the chloride ions, if you're interested in them, would also be 0.35 molar. Now, remember that we probably want to get rid of the big M. So that 0.35 molar means that is moles of sodium over liter. We can actually see both units there. We basically have both of these guys in what we need them. So the moles here would equal our liters, 0.42 liters times the molarity, where I can see both of the units there. That way I can see that the liters do cancel and we are multiplying here. So I lost a 0 there. That's not good. We pop a 0 in there. 0.0420 times 0.35. Going to give us 0.0147 moles of the sodium ions. Any questions on that particular one there? So again, you may come across questions like this where we're interested in just the ions. So you can really use the formula as sort of a stoichiometric relationship to adjust the concentration. Any questions? Okay, so let's take a look then at another one here. We want to know what is the mass in grams of sodium nitrate that's required to make a 2.5 liter solution that has a molarity of 0.15. So take a couple minutes here. Sodium from the periodic table 2299, nitrogen 1401, and oxygen 16. Okay, let's take a look. So once again, if you're not sure, we obviously once again here are dealing with molarity, which is moles per liter. And again, if we check off sort of what we are given, we are again given the molarity and the volume. So definitely starting and solving for moles would be a good spot to do. And that does make sense because if we get to moles, we definitely could get to grams by using the molar mass. So that's basically where we want to start with here. So once again, I'm going to sort of get rid of my kind of big M there and turn this guy into 0.150 moles per liter of sodium nitrate. In this case, my volume is already in liters, so that's good to go. So we'll go with 2.5 liters. We're going to use our molarity really like a conversion factor here, 0.15 moles of sodium nitrate per liter. Our liters will cancel, and at this point, if you get an answer, 2.5 times 0.15 gets you 0.375 moles of our sodium nitrate. So once again, we're close to where we're at. We do need to get over to grams. So that is again going to be our periodic table and our molar mass. That's going to allow us to do that. So we're just going to add up all the parts here for sodium nitrate. That is a 2299 for the sodium, a 1401 for our nitrogen, and 3 times 16 for our oxygen. Going to give us 85 grams per mole. And again, we're going to use that as a conversion factor. So we'll take our 0.375 moles of our sodium nitrate using our conversion factor here, where we will put grams up on top so that the moles cancel. Will tell us we will get about 31.9 grams of sodium nitrate here. Any questions on that calculation? So it's very similar to the calculation you did in the last part of the experiment. So basically, if we wanted to make the solution, we would then weigh out about 31.9 grams. We would dissolve it in water, enough water to give us a total volume of 2.5 liters. When we mix it up, say in your graduated cylinder or your volumetric flask, you would have a solution that has a molarity of 0.15 molar. Any questions on any of that there? So the next thing we're going to talk about is a more dilute solution and really the process known as dilution. So a lot of times solutions do come in sort of concentrated solutions. And when we use them, for example, in the lab, they're pretty much dilute solutions at that point. And really, when we do a dilution, really the only thing that's really added is more solvent. And a lot of times that solvent is water, but once again, it doesn't always have to be water, but water is oftentimes sometimes what is added. So the reason why we will see the concentration kind of go down in this case is because if we look at molarity, and really what it is moles of solute per liter of solution. And remember that the solution is both the solute plus the solvent, which means in the case of doing a dilution, really the only thing that you're changing in this formula is the amount of solvent, which means this guy gets larger, which means the volume part there, the solution gets larger. And the result of that is we see the molarity go down as a result of that, because you'll end up having a larger number on the bottom divided by a smaller number up on top. So when we dilute a solution, we typically will see the molarity come down. The thing that doesn't change, though, when you do a dilution, as you can even see from this formula, is the solute. The solute is really untouched here, which means before the dilution and after the dilution, there's really no change in the amount of solute that you have in there, if obviously all you did was a dilution. Remember, it is a solute that's really sort of the active part of a solution. It is really what is reacting if you should pour something else in there to cause the chemical reaction to take place. So the moles of the solute before your dilution, it will equal the moles of the solute after your dilution. And there is a formula that we use typically for dilutions. And this is a example of how you could do a dilution. This is a volumetric flask like the one you used the other day. You can put a little bit of water in there. Our kind of more concentrated solution could go in next. And then you top it off with water once again to the line, right? And that will obviously make it a much smaller or lower concentration than it started with. So the formula that we typically use to help us decide or figure out how to do a dilution is this one. This is M1V1 equals M2V2. It's the dilution equation. And much like it says there, typically speaking, M1 and V1 are before the dilution. So that typically is your more concentrated solutions. M2 and V2 are typically your more dilute solutions, but it really doesn't matter which side of the equal sign you put them on, as long as you keep the numbers together, it will work out the same. Molarity on both sides here. Obviously, it needs to be a molarity. Volume probably should be liters, but this is one formula that we talked about earlier where if you want to, and you're specifically using this equation, you can leave the volume in milliliters and it will work out okay. And that's because, well, if we just look at our volume here, say we're solving for V2, which would be M1 V1 over M2, we would have molarity times milliliters divided by molarity, which means the molarities will cancel and we would end up with milliliters in this case. So it would work out okay. If you were solving, say, for M2, M1 V1 over V2, you basically would have molarity times milliliters divided by milliliters. Those guys would cancel and you would end up with molarity at the end as well. So this is the one equation where if you want to leave the volume in milliliters, you can, and it'll be okay. Just if you're solving for volume, you'll get milliliters out on the other end. Or if you don't want to worry about it, just convert it to liters, and what you get out at the end would be in liters. The really reason why this works, once again, is when you take molarity times milliliters, you get what are known as millimoles. And when you divide it by milliliters, the millis cancel and it comes back to moles per liter, which is molarity. So that's really why in this case, it does work out. So you will see me probably use milliliters here. And again, it will work out only specifically here. But just to reinforce it, if you are doing like the problems we just did previously, and there's not a dilution and you're using molarity, you need to convert it to liters. Otherwise, you will be off probably based on what they're asking in the question. So definitely molarity by itself, non-dilution situation, 100% should be in liters. If you want to leave it for this equation in milliliters, it will work out okay. There is also sometimes a generic version of this equation that sometimes books and people use, which is C1V1 is equal to C2V2. And C here is just a generic concentration unit, because technically speaking, you don't have to use molarity in this equation. You could do something like percent mass to mass like we did earlier, or percent volume to volume on both sides. So you really could use any type of concentration unit on both sides. So sometimes people will use the more generic version of C1V1 equals C2V2. I would say most people will roll with this one because really molarity is the most common unit of concentration that's used. So a lot of times M1V1 equals M2V2 is usually used a lot. Now, if you're solving for M1, that is typically the more concentrated solution's concentration. If you're solving for V1, that's how much of the more concentrated solution you're using. M2 would be the concentration of your diluted solution, and V2 would be the total volume of your new solution, your kind of diluted solution that you made. Any questions on that there? All right, so let's take a look at one here. What is the volume of a 19 molar, what volume of 19 molar sodium hydroxide must be used to prepare 1 liter of 0.15 molar sodium hydroxide? So take a second here or two and see what you come up with. We're starting with 19 molar sodium hydroxide. We're ending with 0.15 molar sodium hydroxide. There's no other reagent or anything there. So we're basically just going to be adding some water here to dilute it down. So that definitely is sort of our M1 V1 equals M2 V2 situation here. M1 would be our 19 molar. V1 we don't have, so that's sort of what we're looking for. Our new concentration is 0.15 molar, and our new volume here is going to be 1 liters. So in this case, we're going to solve for V1, which means we're going to divide M1 to the other side. And that would give us V1 is equal to M2 V2 divided by M1. Putting in our concentrations here, 19 molar, and we have 1 liter. And in this case, we have M2 is 0.15. That didn't seem right. There we go. Try that again. That is M2 is 0.15. There we go. 0.15. Divided by our M1, which is 19 molar. Here, the molarities will cancel. Will leave us with liters, which is 0.15 basically times 1 divided by 19. Gets us something like 0.0079 liters, or if you want something like milliliters, you times it by 1,000, you got 7.9 milliliters of our sodium hydroxide. So what's that number really represent? That represents that we have a bottle basically over here that is 19 molar sodium hydroxide. And we basically are going to make a new container here. And basically what this means is we should reach in there and we should take out 7.9 milliliters of our more concentrated sodium hydroxide solution into our new container. The rest should be water, right? Would I then put like 1,000 milliliters of water, which is 1 liter? Would I add another 1,000 milliliters of water to this? I would not, because if I did, I would then be at a total volume of 1,007, right, or so. And that is not what I'm shooting for, right? My total volume that I want is really 1,000 milliliters or 1 liter at the end. So a very common dilution question is actually a lot of times, how much water should you add? And to figure out how much water you should add, typically speaking, the volume of the water is V2 minus V1. V2 is like your final volume. V1 is how much of the more concentrated solution you would use. So in this example here, I'll just do it in milliliters. We take 1,000 milliliters minus the 7.9 milliliters we've already put in there. And that means that we really should toss in there about 920, no, try that again. 1,000 milliliters minus 7.9, 992.1 milliliters of water would go in there. So we'd add a 992.1 milliliters of water. At that point, we would mix this guy together really well. And what we should have now is basically 1 liter or 1,000 milliliters of a solution that has a concentration of 0.15 molar. Any questions on that there? All right, so why don't we try another one here? Let's take a look at this. What volume of water is needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar calcium nitrate solution? Okay, so once again, this is a dilution where you have calcium nitrate at both places. Really, the difference is just the molarity. So once again, this is going to be M1V1 equals M2V2. Once again, in this case, we basically have a bottle sitting there that is 5 molar of calcium nitrate. And we want to make a new sort of container there that has 500 milliliters total volume. We'll call that V2. And we will have a new concentration of 0.25 molar, which would be M2. And obviously, this would be our more dilute solution, which would be M1. So we could use the dilution equation here once more to actually solve for V1. Once again, sending our M1 to the other side. So V1 would equal our M2 V2 divided by M1. Putting in our numbers here would get us 0.25 molar. Once again, I'm not going to worry about the milliliters here because it will work out okay in this equation. But if you want to convert it to liters, you can. It would just be 0.5 liters. Again, it'll come out the same in this particular problem. You would end up with 0.25 molar. Our molarities will cancel. That will give us our milliliters as what we're going to end up with. And that would give us 25 milliliters of our calcium nitrate. First off, any question on that? So here, because I did leave it in milliliters, I get milliliters at the end. If you convert it to liters, you would have 0.025 liters, which is again the same thing, basically 25 milliliters. At that point, though, that's not our answer because here we're again looking for water. And that V1 is really how much we would take out of the more concentrated solution and basically toss it in there, our 25 milliliters of it. So once again, to find the volume of the water, we'll take our final volume minus how much of the more concentrated solution we're using. In this case, we are looking at 500 milliliters total minus 25 we already put in there. That's going to give us 475 milliliters of water needs to be added. And that would mean that we would obviously top this off at this point with 475 milliliters of water, give it a nice little mix and shake, and we would end up with a solution that's 0.35. Yeah, either one. You would, you would, yes, but I do get 25 though, right? I think I wrote the wrong number. It should be right. Thank you. It also helps to write the right number, I suppose. There you go. So it would be 5. I did that twice today. All right. So these cancel, but still 25, I believe, right? Yes. So that was good at least. All right. I guess I was thinking the right number, just wrote the wrong one. Thank you. It definitely should be 5 molar. Same question. Thanks. Thank you. Other questions on that? Questions on dilution. So a very common mistake, again, people make is not really reading the question. A lot of times, you know, the question for dilutions is sort of centered around how much water you need to add or how you would make that solution is a very common question. All right, the next thing we're going to talk about then with regards to solutions is our favorite thing, which is stoichiometry. So we've talked about basic stoichiometry problems, also limiting reagent stoichiometry problems using grams and moles. In the previous chapter as well, the gas chapter, we did stoichiometry that involved gases. You can also do stoichiometry that involves solutions. The same rules apply. Pretty much it's the same 4 steps. You need to balance your equation. You need to convert to moles. You need to do the mole-to-mole relationship, and you need to figure out, convert those moles to some other units. Once again, you can also have a limiting reagent situation as well in these type of problems. And to remind you how you know it's a limiting reagent problem is you have enough information to get to moles of each of the reactants. So if whatever they give you in whatever units allows you to get to moles of each of the reactants, then definitely you need to do a limiting reagent problem. If they don't have enough information to get the moles of all the reactants, then it's just a basic stoichiometry problem. You just kind of continue with what they gave you to get there. The really major difference is in sort of solution stoichiometry is this, how we get the moles. So instead of grams to moles like we have done in the past where we use the molar mass, here we use our molarity basically to get to moles. and the moles would equal liters times the molarity. So that is the biggest difference here in a solution stoichiometry problem, is really that step. This step, when you're doing a problem like this, unlike with the dilution we just talked about, once again, it does need to be in liters for sure. Yeah, so make sure that it's in liters. The other difference is kind of like the gas laws problems in stoichiometry, is sometimes at the very end here of the stoichiometry problem, they don't want grams, but maybe they want volume, like liters or something like that. Or maybe they even want molarity. So sometimes on the back end of the calculation, you will also use the molarity equation and either solve for liters or solve for molarity. So those are two common sort of variations on solution stoichiometry. Definitely for sure up front, a lot of times, not all the time, but a lot of times you will use molarity, but you can use it at the end, especially with titration problems. We use it like at the end. So let's take a look at one here together to kind of go through the steps and talk about what's going on here. We want to calculate the mass of solid sodium sulfate that must be added to 250 milliliters of a 0.25 molar barium nitrate solution to precipitate all the barium ions as barium sulfate. We also want to calculate the mass of the barium sulfate. So we're actually looking for two things, but like normal, we want to start with the most important thing in stoichiometry, which is the equation. So we want to know how much sodium sulfate, so that is Na2SO4, must be added to barium nitrate, which is BaNO3 to precipitate out, which means we're going to form barium sulfate. And if it's going to precipitate out, that would probably be a solid. And also calculate the mass of barium sulfate formed, which will be that guy as well. So there we go. So our other guy obviously would be our sodium nitrate coming together, right? So we're going to do a double displacement here. So we should end up with NaNO3, right? And that would obviously be soluble. So we got our equation, which is a double displacement reaction, right? Our two positive guys switch places. Put that there. The next thing that's really important, obviously, in stoichiometry is we want to balance the equation. It's not balanced, so I think we need a 2 there. And I think that might do it at that point. Looks like we're good at that point. All right, so that takes care of really the important part, which is the equation. The next thing that we want to do is take whatever they gave us and convert to moles. The only thing that they gave us was we have 250 milliliters of a 0.2 molar barium nitrate solution. In this particular case, that is the only piece of information that's given to us, which means it really is just a basic stoichiometry problem. And the good news here is we have volume and we have molarity, which once again means that we can have this and this. So we definitely could get to the moles of that. So that's what we want to do. We're going to convert our 250 milliliters into liters by dividing by 1,000 or moving the decimal place 3 places to the left there. Going to give us 0.250 liters. We're going to take our molarity that was given to us and turn it into a more conversion factor of moles of barium nitrate per liter, so that we can see both of the units. So again, that guy is obviously here, and this guy converted to liters there. That is going to allow us to get to moles. So that is really the second step that we want to do. The moles of barium nitrate in this case would equal our volume converted to liters times the molarity, 0.2 moles per liter of barium nitrate. Means that the liters of barium nitrate cancel. I am not interested really in barium nitrate, right? I am interested in, we want to know the mass of sodium sulfate, which is this guy, right? So while I'm here, I could do some stoichiometry, and it is a 1-to-1 relationship between those two from the equation, which means for every 1 mole of barium nitrate, I get 1 mole of sodium sulfate. So that's the stoichiometry part. The moles of barium nitrate will cancel, and that will leave me moles of my sodium sulfate, which if I get my answer will be 0.25 times 0.2, looks like 0.05 moles of sodium sulfate. First off, any questions so far? So really it is our steps that we've talked about previously. We have a balanced equation, we have convert to moles, and we have our mole to mole relationship from the balanced equation. Any questions so far? At this point, I'm looking for the grams of sodium sulfate. So to get to grams now, I will need the molar mass. And if I do the molar mass of sodium sulfate, that is 2 times 2299. That's going to be 2 times 2299 for our sodium, plus 3207 for our sulfur, plus 4 times 16 for our oxygen there. That's going to give me 2 times 22.99 plus 3207 plus 4 times 16. Looks like 142.1 grams per mole. So we're going to use the molar mass there to convert our moles into grams, which will be the final step here of this part of the problem. So using the molar mass we just calculated, we have 142.1 grams per mole of sodium sulfate. The moles of sodium sulfate will cancel, and that gives me 0.05, looks like. That gives me something like 7.10 grams here. So in this reaction, we would have to toss in there 7.1 grams of sodium sulfate to get this reaction to go. And obviously that would be our fourth step here. First off, any questions on any of those steps? We're also looking in this problem for how much barium sulfate we would make, right? So we could do the second part of the problem here by picking it up with our moles of really anything. We could do the moles of our sodium sulfate or the moles of our barium nitrate. So for the second part of the problem, we'll just pick back up here with our moles of our barium nitrate that was given to us. So that is 0.025 liters of barium nitrate. Once again, using the molarity like we did above, I'll rewrite the calculation here, 0.2 moles per liter of barium nitrate. This gives us our 0.05 moles of barium nitrate. In this case, we are interested now in the barium nitrate to the barium sulfate, which also happens to be a 1-to-1 relationship. Obviously, it will not always be a 1-to-1 relationship, but we do see it here. So 1 mole of barium nitrate gives us 1 mole of barium sulfate. I think I could do that math. That's going to stay the same, hopefully. So 0.05 moles of barium sulfate. And obviously, in this case, we're looking for how many grams. So we would need the molar mass now of barium sulfate. Barium there is, what is that thing? 137.3. So 137.3 for our barium. And our sulfate, 3207. And our sulfur 3207, and our 4 oxygens as 16. So that gives us 137.3 plus 32.07 plus 4 times 16. So it gives us a molar mass of about 233.4 for the barium sulfate. So I'll just write down here 233.4, if I didn't miss any numbers here, per mole from the periodic table. Moles will cancel, and we will end up with 11.7 grams of barium sulfate would be produced in this case. That, by the way, would be our theoretical yield, right? The amount that we got from the actual equation. So in this case, we actually had a couple of things we were looking for, kind of two problems in one on this one. But hopefully you could see that it is really the same 4 steps. Even on the bottom here, it is the same 4 basic stoichiometry steps. Obviously, once again, starting with our balanced equation, converting to moles, mole to mole relationship from the equation, and converting those moles into something else. So really the main difference with solution stoichiometry is somewhere along the way, either at the beginning or at the end, or both cases, you will use molarity to get the moles, and then you also will use molarity perhaps at the end to get molarity or to get volume, which is your 2 common things. Any questions on that there?